Okay. Okay, thank you very much. So I'm very glad to start these cycles of seminars on this project funded by University of Padua on physics of data and societal challenges. And the first seminar will be given by Dr. Giacomo Masato. Giacomo is a friend. He graduated here in Padova in 2006 in physics, doing his master thesis in Bologna. He then did his Ph.D. in Reading, London, and then he moved, let's say, to private sector, but always on the research and development field. And very recently, actually, is 1 year or so, he came back from UK and is now working in Bologna, in Illumia, and he's the head of the analytical department at Illumia. And he always worked on modeling weather and climate with different application. And today he will present us basically his work and the main challenges and application that he foresees. And also at the end of the seminar, he might propose some possible also project that can be done by students. So thank you, Giacomo, for being here. And
thank you, Samir. Yeah, switched on. Okay, thanks for the introduction. So Samir already said it. This topic will be about, this seminar will be about modeling weather and climate. I'll try to look at 2-3 main topics. The first one being, well, the first couple actually of topics are actually interconnected. They are linked to each other. So I'll try to explain what I mean when I say the weather problem versus the climate problem. These two are essentially different issues that we generally tackle when we try to forecast and model the atmosphere. Therefore, the approaches that we use and the model capabilities and infrastructure that we use can be also very different. So that will be around 2/3 of the seminar. And then the last bit, which is number 3, would be the energy sector applications. I work in the energy sector since 2015. And during the past 5 to 7 years, we developed with different people models, not just for predicting the weather, but also for predicting how the weather impacts the energy fundamentals. So I'll tell you more when we get to the end of the seminar. So when we speak about weather and climate, we typically, well, everyone really understands it pretty much. Weather is what you would think about a daily change in the outside weather conditions. Today is sunny, tomorrow is cloudy, the day after tomorrow is going to be raining. That's typically weather. So in physics, in mathematics, we may describe it as a high-frequency phenomena, as opposed to the climate, which is, of course, an event, a set of phenomena that typically span within decades or even centuries, and typically entails regions that are much bigger than, for example, a single city. If you are interested in the weather, of course, you are more focused on understanding whether there will be 10 or 15 degrees Celsius in Padova today, and what is going to happen tomorrow. Will be the temperature higher by 2 or 3 degrees or lower. So therefore, high frequency and very small scales. Climate is the opposite. Very slow in time, so low frequency, and very big in space. So let's first face the weather problem. So here I just put a square, which tells you pretty much where we are trying to predict the weather volatility. It's going to be between days, maximum a couple of weeks. What we typically are looking at in this case is what we say an initial value problem. So in order to predict successfully the weather, we need a set of equations that are good enough to describe the mechanics of the atmosphere. And second, most importantly, we need a very precise knowledge of the atmosphere at t equals 0. The better you know all the characteristics of the atmosphere at t equals 0, the better your forecast will be in time. As you know, whenever you progress your forecast, the forecast in reality, what is it? It's a set of differential equations which is integrated in time. So you integrate not just the information, the signal, which is the state of the atmosphere, but you also integrate the error. So that little tiny uncertainty that is associated with the initial conditions where you start integrating the equations. It's like myself giving you 50 different thermometers and asking you what's the temperature in this room. So every one of you may come back to me saying it's around 20, 22 degrees. Let's say 22 degrees. But then if I were to ask you a precision of 1 or 2 digits, the answers will be different. These tiny differences will play a major role in the uncertainty of the forecast 5, 10, 15 days down the line. Because as I said, you integrate the signal, but you also integrate the error. Therefore, the error becomes very big. By the end of this time frame, 10, 15 days typically, the signal-to-noise ratio becomes very, very small. So that's an example, much more complex because that's the Earth. And in fact, this is a picture of the atmosphere for a random day that I picked up a few years ago. That was May 11th, 2018. Here's the North Pole. And then around you have the continents. So North America, the Atlantic, Eurasia, and the Pacific. There's quite a few features going on in this picture. I tried to highlight a couple of those. First of all, this black dashed line and the other one, the white one. These two are what we call the jet streams. What are the jet streams? When you, well, first of all, you know that the Earth is associated with an energy imbalance between the tropics and the poles, because the sunlight, the energy of the sun that impacts the Earth is uneven. That imbalance in energy creates an imbalance in temperature that in turn creates an imbalance in pressure. Because the Earth spins around its own axis, this imbalance creates essentially this flow of air that constantly flows from the west to the east. If you look at the North Pole clearly, this movement would be anti-clockwise. So there are a couple of different jets. One is the subtropical jet, the black dashed line, and the other one, the white one, is the jet stream. That's the one that interests us the most, because, for a simple reason really, because we actually live in the mid-latitudes. Here is Europe, with the UK over there. Here's North America, and then we have Eurasia, particularly the eastern side. So we have China, South Korea, Japan. So all these regions that are highly densely populated sit underneath the jet stream. And the jet stream, as I said, is a flow of air that constantly flows from the west to the east. But it doesn't do it in a straight line. It does it by waving. And these waves, with their crests and their troughs, are essentially creating the weather variability. So if you just fix yourself in a specific region and you just sit there and wait and see, you will see a continuous sequence of high pressure and low pressure, so the crests and the troughs of the waves passing by. Okay? High pressure conditions is what is today. Sunny weather, no wind, no precipitation. Low pressure area, when you have a trough crossing by the region where you are, then there will be typically lots of wind, precipitations, and then of course there will be different air masses connecting to each other. So that's really where the weather forecast comes into place, because at this point in time, let's say that here we are counting, and I highlighted them for you, around 6 to 7 troughs. That means that K is equal to 6, 7. So we have a wave number of 6/7 around a circle of latitude which encompass the North Pole. One of these is this red one here, which is a low pressure area that sits pretty much off the coast of the UK. Now, that's T equals 0. we need to understand what is going to happen to this low pressure area in 2, 3, 5, and 7 days. Now, we know that it will move from the west to the east, because I just said it to you, and that's the average motion of the flow. But then, of course, because the structure of the atmosphere is three-dimensional, the motion of this low pressure area will be pretty much complex. So it may, in its movement towards the east, drift to the north or to the south. It may amplify in magnitude or damp. And all these features are essentially features that you have to capture or forecast in advance in order to produce a good weather forecast. So I said it before, the initial condition problem or uncertainty that you get at the very beginning then gets larger and larger. So that thing that is potentially a big issue has been used more recently in the years to actually produce an ensemble weather forecast, which means essentially probabilistic weather forecast. So rather than launching at t equals 0 a forecast, a single forecast, you actually launch 30, 50, 100 of those. And what do you do at the beginning? You simply artificially change by a tiny bit the initial conditions so that the state of the atmosphere at the beginning is very similar but not identical. And then you integrate simultaneously these 20, 30, 40, 50 members, which are essentially forecasts, in time to understand how different they will be down the line. So this will allow you to get a sense of the uncertainty that is associated with the forecast itself. That's an example produced by the Met Office UK, where you have a forecast in rainfall, in precipitation over the UK itself. And here are these little frames are nothing else than different outputs of each single forecast member, which of course will produce a geographical distribution of the precipitation of the UK, which will be in some cases very similar, in others very different, and therefore out of this ensemble then you can produce a probabilistic forecast. So you will not say anymore there will be 50 millimeters of rain in London in 10 days' time. But there will be, for example, a 70% chance in London in 10 days' time to get rainfall accumulation which is above a certain threshold, for example, 10 millimeters. Okay? So clearly the information is less precise, but it's probabilistic in its nature. Therefore, it gives you an idea of how big is the uncertainty and how spread out is the uncertainty itself. Okay? So that's the way weather forecasting is actually tackled in general. The models are called NWP centers or models, which stands for numerical weather prediction. And this at the top is a very, very crude simplification of what has been the development of this model since the very beginning of the 20th century. So it all started off via very simple radiation models that were only looking at keeping constant the radiative equilibrium of the Earth, which is clearly talking to the space, right? So that was the only constraint that the very first model were actually caring about. Then the more they improved in the knowledge of the physics and maths behind the atmosphere and the oceans, and the more they perform better and better computational machines, then of course they could do further steps. The very first step was clearly the introduction of dynamical cores, which are still the very core of the models, nowadays models. So the dynamical cores, which is a crude representation of what I was saying to you before, understanding whether this low pressure area will move in a specific direction is essentially a task of the dynamical core of the models. But then they went even further. They coupled the ocean, which of course is another fluid with different characteristics. But then it has to be coupled against the atmosphere. So you need to make sure that whatever the weather forecasting is doing for the atmosphere gets coupled and interacts dynamically with what the ocean is actually doing. And then later, towards the end of the 20th century, there were the land, sea ice and land surface mechanics. Think, for example, of the albedo processes. The albedo is very important because it allows you to understand how much energy is scattered back into space. And at the same time, the land and surface towards the atmosphere coupling is also very important. Latent and sensible heat exchange continuously between the surface and the atmosphere. These are very useful to get your forecast very precise when you need to really measure something like, for example, temperature in a city. Think all the sensible and latent heats, fluxes that are exchanged by the morphology of a city towards the atmosphere, which is very different from the countryside, for example. And then aerosols, vegetations, chemistry as well. So I won't get into all the details because otherwise it takes too much. But you have to just bear in mind that all these processes are actually now modeled typically in an explicit way. They're not parameterized, but they are explicitly modeled in all the different boxes of these, what we call general circulation models, which are like this. Okay? You just grab a little bit of the surface of the Earth, you scan it three-dimensionally, so you move it from the bottom to the upper part of the atmosphere, and then of course you grab and you divide it in grids, and then you apply your computational scheme, essentially, which is what they do on a daily basis with the supercomputers. The other problem is the climate problem. I mean, it's very different, as I said before. Here we're not interested in understanding from t equals 0 to t equals 5, for example, days, what is going to happen to the different characteristics of the atmosphere. But we're rather interested in understanding how the entire globe changes if we force from the outside the globe, the atmosphere, the oceans, towards a specific direction. Think, for example, of the global warming issue. The atmosphere is warming. Why is it warming? What is it allowing the equilibrium of the energetic equilibrium of the Earth to change in time? That's a very typical climate problem because we're not looking here at t equals 0 and understanding from the initial conditions what is going to happen afterwards, but we're actually forcing the system, in this case, by increasing the greenhouse gases efficiency, and we're forcing, therefore, the energy balance of the Earth to change. That's a forcing that is imposed from outside the system, let's say so, into the system in order to change its equilibrium. Now, that kind of problem, which of course is used to tackle issues like climate change, is also used partially to try and forecast the weather beyond this couple of weeks threshold that I was saying to you before. So after 10, 15 days, you're going to lose the signal out of the classic method that you have for forecasting the weather. So how can you possibly try to forecast successfully, say, a seasonal change in the weather rather than a daily change in the weather? What is going to happen to Italy or to Europe in a couple of months down the line? It will be colder than average, warmer than average. In order to answer to these questions, we need to take into account the boundary condition problem. How do we do that? By knowing that in the atmosphere there are certain forcings that are actually pushing the state of the atmosphere in certain directions. One of these forcings is called the El Niño. Here we're looking at the Pacific. This box over here, this three-dimensional box over here at the bottom is a crude representation of the ocean. Here at the surface of the ocean we have a red blob, which is essentially telling us that the waters of the Pacific are very warm. They typically are between 27 and 30 degrees Celsius. But the important bit of information to retain here is the fact that at the surface, along the equator, winds are actually flowing from the east toward the west. These are the trade winds, and they always do so. What they effectively do is imposing a stress on the upper part of the ocean. So they pile up physically the waters from the eastern side of the ocean towards the western basin. Yeah? Doing so, they create an imbalance between the eastern part of the Pacific and the western part, in a way that always in a specific ocean along the equator, you will always find that the temperatures at the surface of the water are always much warmer on the western side as opposed to the eastern side. Now, there are, however, sometimes wind stress events that are actually pushing the wind direction from the opposite, okay? Rather than from the east to the west, that do from the west to the east. I won't get into the details again because unfortunately we don't have much time to do a proper lecture on these things. But if this happens, of course, you're going to modify substantially this kind of circulation. Rather than pushing the warm waters from the east to the west, you do rather the opposite. And therefore, during El Nino events, which is what it is about, these westerly wind gusts that are going to push the water instead towards the central part and the eastern part of the Pacific, you tend to have lots of convection. Why? Because where you have warm water, you have lots of fuel, right? You have the heat, you have the energy. Therefore, the air passes that happen to find themselves over the warm water, they're going to be pushed to the top of the atmosphere. They are lighter, they're going to be pushing to the top. At that point, they will condense and precipitate in form of rain. But the bit that interests us the most is that in this case, and that's really this funny representation of this cumulus, that's a cloud, clearly, or less clearly, but let's say it's a cloud. So you have an ascending motion here of air towards the top of the atmosphere, which is called tropopause, which sits at around 10 kilometers. Now, that is literally, you have to look at it, so think of it like a literal lid, a physical lid that sits at 10 kilometers. When the air gets there, it pinches the top of the atmosphere. It's like tossing a rock on the surface of a pond. As soon as the rock hits the surface, then the information, the wave, radiates around the little rock. Okay? That's exactly the same thing that happens here, just reversed. Yeah? The air gets pushed from the bottom, it pinches the top of the atmosphere, and from there, it radiates around. How does it radiate? In such a way. These are preferred pathways through which the signal that is generated in the center of the Pacific gets transferred around the atmosphere. These are these red and blue blobs are nothing else but positive and negative anomalies of a wave. So once again, in a two-dimensional form, they are actually troughs and ridges. And they're doing exactly this job, grabbing the information, the signal that it got pushed up from the air in the tropopause in the center of the Pacific around the globe. These are a couple of examples that are actually found with a PCA analysis by looking at real data. So you just look at two-dimensional maps in the past for 50 years. You apply the simple PCA analysis, and what you get out of this, it is kind of features. So the atmosphere is not random at all. It's not chaotic in a pure sense of the word, because there is a signal which is clearly much buried into the noise, but it's there. So this analysis, the PCA, like others, EOFs, clustering analysis, are doing exactly this job, grabbing the variance, explaining the variance out of the noise. And that's exactly what it does here. So these are statistical models. They are not physical model or mathematical model in a strict sense, because they don't explicitly solve differential equations as a function of time, but they actually grab the forcings, like El Nino. They study statistically the teleconnection, how the signal propagates from a remote location to a target location, and then they essentially train the model in such a way, because they give it the information to how to interpret the atmosphere in any given point of time. So as I said, well, I already said the last point. What we need for a good statistical model to try and forecast the atmosphere, say in a seasonal or sub-seasonal time frame, which is the S2S that sometimes you see in my slide. This S2S meaning seasonal to sub-seasonal. You need this kind of setup. you need a large data set to train your model. And that's typically done by using the reanalysis data. I don't know if you ever come across them, but reanalysis data meaning that what we get in the past, first of all, we need large data sets. So how do we construct them? We grab the information that we collected from the past via radiosones, via satellites, stations, aircrafts, ships, and anything you can really think of. And then what we do is actually using the very same model that I was explaining to you at the beginning, the classic mathematical physical model, and then we produce a hindcast. Okay? We let them run with the initial conditions in the past that we knew with some the degree of certainty, and we let them run in the past. We produce a hindcast. The hindcast is the basis of the reanalysis. The big job is, in fact, fill the gaps, because the information that you got from the past are sparse in time, because they're not always there. And the more you go back to the past, the less you find. And they're sparse in terms of space, because there are big holes. So with a model like that, you're going to fill the holes. And therefore, nowadays, what we typically have is a spectra of different reanalysis data sets, which are going back to the 19th century. So we have pretty much 150, 200 years of data. Okay? So that's pretty much good enough to train a model. Then, of course, you use your statistical framework. It can be very different. It can be a very simple multi-regression analysis model. It can be typically what we use in our field is the method of the analogs, which is looking at the present condition of the atmosphere and then scanning back in the past to actually search for very, very similar pictures, frames, as simple as that. And then once you identify the prime analogs, then of course you know what is going to happen next. So that's the framework and the models that are typically used to produce a seasonal to sub-seasonal forecast. Is everything clear so far? I didn't say it at the beginning, but if you want to stop me at any point in time, you just tell me, and I'm more than happy to answer questions on the fly. So the last bit, last 10 minutes, I'm going to show you specifically what we do when we use the weather modeling into the energy sector. Now, to set the scene, I put this slide just to make you understand why the weather has become so key in understanding the energy world, specifically in Europe. That's a figure that shows you the electricity production in Germany. I picked Germany because it's by far the most important country in Europe. So it is really a good proxy if you want to see everything else. And this stack bar plot is nothing else than the total amount of electricity produced over the years since 2002 up to present, pretty much, for different sources of electricity. So at the bottom, you have the base, what we call the base load, which is the nuclear electricity production, the one that always goes on and never really gets switched off. And then you have the fossil fuels electricity, which is this bit over here, the gray and pale yellow, orange over here. And then at the very top, you have the renewables, meaning to a first order, wind and solar electricity production. I draw these white lines simply to highlight the fact that since 2010, there has been a significant change in the stack of the electricity production. 10 or 15 years ago, the electricity was essentially produced out of nuclear and fossil fuels, and that was it. Now, the electricity in Germany is produced by, to a first order again, fossil fuels and renewables. And the ratio between the two is very much equal to 1. Okay? Why is this important? Well, first of all, because we produce cleaner electricity. Second, for us, it's very important because it means that the electricity that you produce and that you then send in order to meet the demand of electricity that each country has got comes from the weather. And the weather, as we know, is by nature volatile. So if you know how to predict and describe the volatility of the weather, you know also how to describe and predict the volatility of the energy system. Okay? Bear in mind that this is just the production side from the electricity. There is also the demand, and demand is historically also linked to the weather via temperature at the ground. Think of cold winters as opposed to mild winters. The difference in demand will be very, very strong. Same applies, and it will apply even more so in the future for summers, because summers will become, as we progress in time, warmer and warmer, and therefore the air conditioning demand will become one of the most important sources of electricity load. Okay, so this means that there is a lot of from the energy sector, there is a lot of desire and need to understand the weather volatility, and that's where we come into place. Okay. How do we do that? Again, by trying to maximizing the variance of the weather variability. If we need to grab the signal out of the noise, we need to apply some techniques whereby we grab the signal. And this, once again, is a clustering technique. It's a k-means. So we, a priori, decide the number of clusters that we want. We put 4 seeds. We look at, as a geographical domain, at the Euro-Atlantic sector. And here we derived 4 different regimes. Where you see red is high pressure. Where you see blue is low pressure. Okay. So these are very well known in the community, clearly in the weather community, weather regimes that are typically found over the Euro-Atlantic sector, which means that if you were to look at the weather every single day for the next 40, 60, 90, 360 days, what you will find is that the weather tries to get trapped by one of these regimes, the weather variability. Okay? The black arrows are mine. So for each slide, if you ever go back to them, there is the source. If you can always outsource the figures and the papers. So the black lines are mine and are simply showing you where the main direction of the wind is. So around the high pressure, the wind rotates clockwise. Around the low pressure area, the wind rotates anti-clockwise. So in this case, when you have a high pressure over Greenland, which is what we call NAO minus, the negative phase of the North Atlantic Oscillation, then you have the cold air coming from Russia, hitting Scandinavia, the UK, and then moving into the Atlantic. Here the air becomes very warm, and it moves towards the Mediterranean. So when you are in a negative phase of the North Atlantic Oscillation, you are very cold over Northern Europe, but very warm over the Mediterranean. Likewise, if you look at the different other figures and you check how the high pressure location shifts, for example here, this regime is called Scandinavian blocking, which means that you have the ridge, the high pressure system sitting over Scandinavia. In this case, the cold air will come from Russia and will hit continental Europe and Italy. So Italy will be much colder over a Scandinavian blocking regime rather than a negative phase of the North Atlantic Oscillation. So once you create the framework, these 4 regimes, then you know how to characterize the weather variability. And these, out of a paper of a colleague in Reading, are the impact on energy, on electricity that you get out of the 4 regimes. So the regimes are from left to right, positive and negative phase of the North Atlantic Oscillation, then you have the Scandinavian blocking, and then the Atlantic ridge, the 4 regime. And here you can see, for example, for wind is actually maximized over the UK when the NAO is positive. But it is minimized over the UK and Germany when you have the Scandinavian blocking. Okay? Likewise, you can check what maximizes and minimizes the solar power production out of these 4 regimes. And at last, you can also see how the temperature at the surface responds when you are in a specific of these 4 regimes. As I said before, and unsurprisingly, with the Scandinavian blocking, continental Europe and Southeast Europe gets very cold. With a negative phase of the NAO, second column, it is Northern Europe to be very cold. Now, if you put together all this information, you can have a very crude, if you like, but very punchy knowledge of the state of the energy balance for Europe. Okay? You put the pieces of the puzzle all together, and what you find is that this kind of figure over here, if you just focus on the first row, these are once again the 4 regimes, NAO plus and minus, Scandinavian blocking and Atlantic ridge. This is a summary of energy production. That's the summary from the demand, consumption of energy, and that's the difference between the two. So with a positive NAO, so the regime on the left, then your shortfall is very negative, meaning that there is very little demand, but lots of availability in terms of production out of the renewables. So your energy system is out of equilibrium in a direction, and is also out of equilibrium in the opposite direction when you have the Scandinavian blocking, because you do have lots of demand, which is over here, but you don't have lots of renewables production. Okay? So no electricity to be provided, but lots of demand that requires it. So the shortfall would be strongly positive. So the system will be very much unbalanced under one of these two regimes in the opposite direction. If we know how to predict, for example, the regimes, and we know how they impact, because we know the energy system, then of course we can do many different things. We can produce a forecast on the energy imbalance itself. We can produce a forecast of the energy prices. And that's very important, because if you, for example, own an asset, you own a wind power or solar power wind farm or solar farm, then you need to know in advance how your production will be impacted, because this will generate different profiles in terms of the economics, as simply as that. Okay, so that's one of the examples that we actually employ in order to understand how the weather variability gets translated into an energy system variability. Yeah. These are typically between 1 and 2 weeks, okay, relatively short in time. So you can actually try to predict them with a classic approach, with an NWP model. So that was it pretty much. Now I just put a couple of slides just to let you know what the projects that we are working on at Illumia. Specifically one of those, which is this. That's one of the things that we are developing as we speak, which is what we call an artificial intelligence GCM, general circulation model. Just because of what I said before, that kind of setup is really keen to have an artificial intelligence type of model. Okay, we do have the data set to train. We do have a machine learning technique to use, and therefore we can try to forecast the weather with this kind of approach. So we have been working with Cineca in Bologna. Well, we're starting the project as we speak. So we just hired people in order to start to put the foundations of this project. So at the moment we don't necessarily have any open position or anything like that, but it is a big project which will take us time. And therefore, I foresee opportunities over here. So if any of you thinks that at any point in time in the future, this is something that is of interest, then of course, more than happy to talk further. The other stream of development is what I just said. Developing this set of models that are actually translating the weather information into an energy information. This is one example of what we do, once again, internally at Illumia. Before I showed you a very crude representation with the 4 regimes. Here we do a much more detailed analysis. That's full of figures and information, and most of it is very tiny, so I understand it's not a very friendly slide. But that's the forecast that we launched today in the morning with the model. And these 3 columns are actually a weather forecast for Europe, starting from the from week, what we call the from week, so week starting next Monday, up to week +3. So we do have a proprietary model which predicts the weather up to week +3. These 3 columns are simply the 3 main clusters of the forecast, because as I said before, you typically produce an ensemble forecast. So here are 3 clusters, 3 different clusters that are shifting the forecast in 3 main modes. And here on the right, for each of these frames, you do have a phase space plot where along the x-axis you have the supply, the anomaly in supply for electricity, renewables, and then along the y-axis you have the demand, so how much will be consumed. And depending on where you are on this plot, whether you are on the bottom right side, on the top left corner, your system will be unbalanced in a different way. Top left, not supply, lots of demand, what we call a bullish scenario, whereby the prices will increase. Bottom right, lots of supply but no demand, a bearish scenario, whereby prices will tend to be subdued because you are imbalanced in the opposite position. So we give this to the end users. The end users look at them. They can run the numbers if they want to have a more specific and quantitative analysis, and then we predict the energy system in such a way. So that's the other stream of development that we constantly improve where I work. And once again, it applies to what I said before. If you think this is of interest, I'm happy to talk on a one-to-one basis. And that's it.
Thank you, Giacomo, for the very clear talk. Questions? Yes? I can use this one. I can talk
So you show the two unbalanced situations, but because you didn't show balanced situations, I have the idea that it's more common to have unbalanced, or it's just because you focus on that?
So there is that a question? So there is always a form of imbalance. Even well, what I highlighted for you was the two extremes. Okay, so the two outliers, if you like. First of all, these outliers are outliers in terms of the magnitudes, but not in terms of the frequency of occurrence. It's very typical to see the positive phase or the negative phase of the NAO, and for example, a Scandinavian blocking. As we speak right now, today we are in a negative phase of the NAO. I don't know if you look at the news in the last couple of days, but London was actually under 5 to 10 centimeters of snow. Here we are pretty much in spring. So and that's really today. And in a couple of weeks' time, there will be a Scandinavian blocking potentially. So these are not infrequent cases. But even though these were infrequent, the other scenarios, which are clearly not outliers in terms of the magnitudes, are always there. So there is always, even though tiny, a degree of disequilibrium in the system. And the system is never, by definition, in equilibrium. It's always trying to find the equilibrium, but it's never in equilibrium. The equilibrium would be there if we had the capacity to store the electricity.
Okay, that was produce. My question. Is typically it's been negative situation, right? So like, because we don't know how to keep the energy and use it later, then we are in trouble in this sense.
Yeah, well, the big caveat of this, yes, it is that there is always a disequilibrium. This will be not entirely, but to some extent pretty much resolved when we will have storage. But electricity storage, it's in its infancy in terms of technologies. You can do it at a very small scale. In your house, you can do it, and you can do it right now. But once you have to scale up that kind of setup to Europe, it will take years, possibly decades, if you want to be pessimistic about it. So we'll have to live with this for much longer.
Maybe just a silly question. First of all, why is there a constraint like a circle for the supply-demand? And okay.
Yeah, well, that's a standardized index. So it's adimensional, and it was simply standardized by some means, like, for example, dividing standard deviation. So essentially, what we're trying to do there is constraining the imbalance into a circle which is of radius 1, essentially. But these are data that go back to real fundamental data. So this data will then be mirrored into a specific amount of electricity produced or requested.
Yeah, and the real question is on a larger time scale, so about the climate, why do you consider equilibrium. So I mean, as soon as I get, you spoke, if you perturb the system, then you see how the Earth will react to go back to equilibrium. So why do you use equilibrium?
Well, in that case, when I was showing you the slides of the El Niño and the propagation of the system, what I wanted to stress was the equilibrium thing is more related to climate timescales, okay? When you need to really search for the energy balance of the Earth. So in that case, for example, the energy of the sun increases, and therefore the Earth, in order to really adjust for this imbalance, will increase its own temperature, okay? That's the search of an equilibrium internal to the system. When it's down to the S2S approach, so the seasonal to subseasonal, I would tend to highlight more the fact that, more than the equilibrium, the fact that you actually impose almost an external condition, although it's not external, because clearly El Niño is within the atmosphere, but you create a forcing, okay, within the system, and the system has to react somehow, because that forcing will produce a signal, and that signal will have to propagate. So that's the very key of an S2S forecast, the idea of the forcing imposed, and the fact that the signal propagates around. Is that?
I thank you for the talk. I have a couple of questions. The first is somehow methodological, because at least to me it's not clear why would we need to empower our prediction by artificial intelligence tool. Because as far as I understood, we have all our set of differential equations that we can somehow integrate. I mean, because I think you can get pretty compatible predictions between artificial intelligence and the differential equation approach. So my question is, you are getting your prediction in a more sustainable way for the business, let's say, because you can forecast on a shorter time scale. They are more ready to use. This is the first question. Then if we have time, the second. Thank you.
So there are 2 points that are relevant to your questions. The first is what you hinted at the end of your question. So in the 7 to 10 to 15 time frame, you're right. There is no need to have a different model, an artificial intelligence model. The only need that you have there is actually because it's much more efficient than the classical models. You're going to produce a similar or comparable in skill forecast with a significant amount of time and computational power. So that alone is already a massive change in terms of what decision you will take in the near future. I'm not saying that the classic models are useless in that case. They're very, very good, and they will use for many, many years down the line. But it's good to know that there is an alternative method that can be much more efficient from an energy and computational power perspective. The other point is that once you move beyond the 10 to 15 days threshold, that classic approach gets useless. And therefore, you need something else. You need a statistical approach. And then when you need when you are after a statistical approach and lots of data, because the reanalysis data are nothing else than 2-dimensional maps. In the past, that machine learning method is just screaming to be used.
But I mean, the question the point to choose artificial intelligence over ODEs and whatever is that, as you said, after a couple of weeks, ODEs are not trustable anymore.
Correct.
So I don't know if it is something you reached for, but isn't there the possibility to merge the 2 approaches? I mean, because otherwise it will be equivalent to say, okay, ODEs are quoted right, on a short time scale, but on long time scale I have to trust some kind of fancy algorithm or whatever.
Well, they're already doing what you're suggesting. So once you're there, once you move towards the monthly time scale, when the differential equations become, let's not say useless, but as I said, the signal to noise ratio gets very, very, very small. then what they're doing at the moment is actually trying to merge the two systems, the two approaches, okay? But you just have to remember that the more you move towards the right, the more your initial volume problem becomes a boundary condition problems. So once you are in the realm of a boundary condition problems, you can get the best ODEs that you like and the best initial condition that you like, but it won't matter a single inch to a good forecast.
I was wondering how well the temperature is actually related to the energy demand, because I can think of it as through heating, but if heating happens through gas, then why should temperature be related to energy demand?
Well, energy production, which is, well, first of all, well, you're partially right, because particularly in winter, when you have to heat up residentials or industries, then lots of it is done by gas. But not all. Part of it is done by electricity. Okay. Also, in order to lighten streets and anything else really that is not heating a place, that is done via electricity. So temperature is therefore very well connected to electricity. Also, electricity is produced out of renewables and out of gas. If renewables are larger or smaller, then of course your electricity will be produced less or more by non-renewables or renewables sources. So the correlation is definitely there, but you're right on the point. The correlation is much higher for gas than electricity in winter. When you move to summer, that's it. It will be even more so, as I said. And there are so many aspects that I couldn't really cover, but for summer, it's not just a matter of how much hot weather there will be in the future. Think, for example, of France. France produces 80% of its energy out of nuclear, but it's a very old fleet. It's a fleet that was built originally in the 50s, so it's got 70 years now. It's essentially at the end of its cycle. And these nuclear power plants, some of them are constantly closed because they are unsafe. So they rely on a fleet that is pretty much at between 50 and 60% of its theoretical capacity. In summer, what you have the heat wave, so everything gets warmed up. There is lots of requests of electricity. And at the same time, you cannot run your power plants anymore. Why? Because if it's very warm and hot for many days, it means that there is a lot of evaporation out of the surface of the water. Therefore, you're going to decrease a lot your reservoirs. The water in the rivers will be very low. At that point, there is a certain levels through which it's absolutely illegal to run a nuclear power station because it will be completely unsafe. At that point, you switch off your nuclear power plant. You cannot switch it on in a couple of days. It will take weeks to do it the other way around. And what do you do in the meantime? So these imbalances, which are pretty much focused on the winter, were to be associated with winter kind of ideas, it will be even more so summer problems.
Thank you. I just wanted to have a quick question. At some point you showed some k-means clustering, right?
Yeah.
And you got that through reanalysis data for the last 200
Correct.
or so years. I was wondering, so each cluster is associated with a given probability of a tiny time point of you finding yourself close to that cluster, right? Has this changed in the last years? So, or is the relative persistence of the cluster stayed the same, especially in recent years where things are changing?
That's a very good point. These patterns are always there. So if you were to look at the 50s, past century, you will still find, and you were just to apply the k-means to a 20-year span a century ago, you will still find them, but not identical as they are. The center of mass would be slightly different. For example, north-shifted rather than south-shifted. And why is so? Because inherently, the atmospheric system is never the same. And for example, a thing like global warming, which is not just a small change in the imbalance of the energy equilibrium of the Earth has got a huge and thousands of different feedbacks. One of those is actually shifting the jet stream that I was talking about at the very beginning of the talk. If you shift the jet stream, which is the waveguide through which these ridges and troughs are actually brought about, then of course you're going to shift also the variance of these weather regimes. So you will find them, they are robust, but they won't be the same.
Okay, so if there are no further questions, we thanks again Giacomo. And the next talk will be probably in mid of April, and will be about food security. We have a person from FIO that will come to visit us and give a talk about food security and how to use data to actually models and understand the evolution of food security around the world. So I will, of course, advertise the talk in time, and also I'm sorry that this talk was advertised just a week ago, but we rush a little bit. So thank you again for being here. If some students want to come here and talk with Giacomo, just come. Okay, thank you very much. Bye.
Thanks.